Good afternoon, everyone. My name is Laayati, a research and development engineer at the Green Tech Institute. Today, I am here to share with you our pioneering approach towards energy management in microgrid using the Tabu search-based optimization method. Today, we will navigate through our research journey on energy management in microgrids. We begin with an introduction to the problem statement and a review of related works. Next, we'll outline our research objectives and present our methodological approach. Then, we'll delve into our models and problem formulation to illustrate the pseudocode for the Tabu search algorithm and discuss the practical aspects of our implementation. After this, we'll present our results and offer a comprehensive discussion. We will wrap up with the conclusion and discuss potential avenues of this future work. In the era of renewable energy transformation, we are confronting the challenge of effectively managing these resources in a microgrid environment, which is hereby complex due to the unpredictable and the variable nature of the renewable energy sources. To address this, our team has formulated an optimization problem or model that strategically aims to minimize the total cost of energy consumption and generation. Employing the Tabu search algorithm, the unique algorithm leverages local search techniques coupled with a memory-based mechanism, thereby circumventing the trap of local optima and facilitating the deviation of high-quality solutions for our energy scheduling problem. Microgrids, a small-scale power grid that operates independently or in conjunction with the area's main electrical grid, have been gaining increased interest due to their ability to mitigate grid disturbances and contribute to energy efficiency. However, the optimization of microgrid operation, especially those involving diverse renewable energy resources and storage systems, presents significant challenge. We are dealing with a complex issue of handling variable energy production from sources like wind, solar, and managing energy storage and demand. Furthermore, the problem escalates then when we consider the economic aspects, aiming to minimize the costs while meeting energy demands. This study addresses these challenges through the implementation of a Tabu search algorithm method for energy management in microgrids, providing an innovative solution to this complex issue. Energy management in microgrids is rapidly evolving field with a lot of research interest. Current state-of-art solutions typically revolve around advanced optimization algorithms and artificial intelligence techniques to achieve efficient energy management. Solutions include the application of various meta-heuristic algorithms like the genetic algorithms, particle swarm optimization, and others to solve the complex optimization problems presented by microgrid. Furthermore, the introduction of machine learning and AI techniques has been added a predictive element to the management of these grids, allowing for more efficient use of renewable energy and storage capabilities. This table represents some of related works of our main problem. So, our primary objective is to innovate energy management in microgrids. We aim to achieve this by developing and implementing a Tabu search optimization algorithm. This algorithm is intended to navigate the complexities of energy supply and demand efficiently across both grid-connected and standalone operation modes. We model our energy management problem as a mixed integral nonlinear programming model, encapsulating all necessary constraints that align with the real-world microgrids operations. To validate our approach, we will implement this algorithm in a specific microgrid scenario and critically analyze its performance against existing energy management solutions. Metrics for this evaluation include the total cost of energy consumption and generation, the usage of renewable resources and CO2 emission. This finding from our research will hopefully simulate further studies in this field, providing valuable insights for improving microgrid energy management systems. Our methodology introduces a unique approach to optimize energy management in microgrids using MILP model to handle constraints and complexities. This model optimizes cost, supply stability, and renewable energy use. The heart of our methodology is the Tabu search algorithm, known for its efficiency in solving complex optimization problems. We test and refine our model and algorithm using a specific microgrid scenario, ensuring an effective solution for complex microgrid energy management. Then, to do this, we start by problem modeling, objective optimization, Tabu search application, customized algorithm, iterative optimization, then validating and testing the algorithm. Then we will proceed to a data-driven fine-tuning approach. The objective function represented in this equation are the prices of photovoltaic, wind, hydrogen, battery, and grid energy, respectively, in hour G. The SPVG, SWG, SH, SB, and SG are the binary decision variables that represents whether the corresponding system is connected to our grid in the hour G. SBG plus 1 represents the absolute value of SPG plus 1, which is equal to 1 if the battery is discharging, or equal to minus 1 if the battery is charging, and 0 if the battery is not connected. In our problem formulation, we ensure that the model is bound by several practical constraints to make the solution applicable in real world scenario. For example, the energy balance constraint, which means the total energy produced or bought must match the total energy consumption at every time point. Also, we have the maximum energy constraint, which is the power output from each energy sources must not surpass its maximum limits, ensuring we do not overtax any source. The battery state of charge constraints and the hydrogen state of charge constraints are the energy stored in the battery and in the hydrogen system must remain within the minimum and the maximum storage capacity limits. Also, we have the battery charging and discharging constraints, which that the rates at which the battery charges and discharges must align with its specific rates to ensure its longevity and the optimal functioning. The same goes for the hydrogen system. And at last, we have the grid connection constraints. This represents whether the grid connection is available for energy import or export. Grid interactions should be conducted only with those periods to maintain the grid stability and to abide by regulatory norms. These constraints are essential for accurately capturing the operational characteristics and limitations of the energy sources, storage systems, grid interactions. Thereby ensuring the derived solution of practical and implementable. As presented in the code of the algorithm, starting by initializing the Tabu search algorithm, the Tabu list size, the maximum number of iterations, the initial solution, and the neighbor structure are set. The initial solution is evaluated and its objective function value is calculated. The current solution and the best solution are set to the initial solution. And the Tabu list initialized to an empty list. The selection of the best candidate solution can be based on various criteria, such as the quality of the solution, distance from the current solution, or the combination of both. The Tabu list can be implemented as a queue or a set, where the solutions are removed after a certain number of iterations. The performance of the Tabu search algorithm depends on the choice of the neighborhood structure, the Tabu tenure, and the termination criterion. The algorithm is often combined with other meta-heuristic techniques, such as genetic algorithms that we will improve in the future work. In each iteration, we are updating also the maximum energy limits, the state of charge of the battery, the hydrogen, and also the binary decision variables, because we have to take it into consideration, because it changed our battery or hydrogen system, or SOC of our systems. So to implement our algorithm, this is the flow chart of the previously discussed algorithm, and also this is the first scenario that we use to validate our algorithm and to calculate the performance of it. In future work, we will test it on variable scenarios and study each limitation in each scenario, and also will compare its performance with other meta-heuristics or other optimization algorithms. So our Tabu search optimization process takes multiple iterative steps. We explore the neighborhood of the current solution, evaluate each neighbor, and select the best solution that's both effective and novel. Throughout the scenario presented earlier and the energy cost and the decision states, we present the test scenario including various energy sources and how the algorithm makes hourly energy management decisions in the decision states, and also calculating the energy costs in each hour. In future work, we will shrink the time limit, and also we will add more investigations on the grid stability, etc. The figures represents our algorithms effectively finds the optimal solution within just 20 iterations, and after which it stops making significant improvements. For the future work, we intend to extend on our research on microgrid energy dispatch, examining other meta-heuristics as explained earlier, new optimization strategies, and issues of overloading and surplus management. In conclusion, this research article presents the Tabu search-based optimization approach for energy management in microgrids, which can effectively handle the complexity and uncertainty the energy surplus, or the energy supply and demand in the grid, connected and standalone operation modes. The proposed methodology formulates the energy problem as an MILP model with a set of constraints and applies the Tabu search algorithm to optimize the energy management strategy by minimizing the total cost of energy consumption and generation. The experimental tests or experimental results are under test, and the simulations show that the Tabu search algorithm have a good performance. The research provides valuable insights in the design and the optimization of sustainable energy management systems. The proposed methodology can be further extended to address other challenges in microgrids energy management, such as uncertainty in renewable energy generation and integration of energy storage systems. Further, research can also explore the integration of machine learning, artificial intelligence techniques to improve the performance of energy management systems. So in the future work, we will test and compare alternative meta-heuristics, explore new optimization methodologies, given a detailed analysis of overloading, surplus, and load prioritization, test the solution across varied scenarios, and incorporating AI and machine learning methods for enhanced performance. For example, using the neural networks to optimize or to solve this optimization problem, or to enhance the performance of this algorithm, the Tabu search algorithm. These are the references of our work. Thank you so much.